Welcome to Axor, Galactic Observatory, where we enter how Magnetars are really born inside brightest explosions. First, the supernova blinds the eye while the true engine vanishes beneath expanding light and debris. The explosion misleads because Magnetar birth happens deeper down where collapse rotation and magnetic violence converge. Not every neutron star becomes a Magnetar, only remnants crossing magnetic thresholds pulsars never truly reach. The deeper trigger is iron, where fusion fails and a massive star's balance collapses within seconds. What matters is the imploding center where density, heat, and angular momentum compress a city-sized remnant. Before the blast settles, everything narrows into a few brutal seconds when ordinary outcomes begin diverging. Those first seconds decide everything, fixing whether convection spin and field growth stay ordinary or extreme. Fast rotation is power because only a spinning core can drive dynamo amplification into Magnetar strength. Fallback can rewrite the birth, feeding the remnant, spinning it up and strengthening fields after bounce. Yet the origin remains contested with Dynamo's fallback and pre-collapse mergers all competing to explain Magnetars. So the question widens from one mechanism to a hidden architecture of fields, histories and survival. The field we measure is incomplete because buried and tangled interiors may store the real violence. Birth leaves scars across the sky through fractured crust. Fierce flares, disturbed ejector and fleeing companions. Some of the brightest explosions may need Magnetars powering superluminous supernovae and stubborn afterglows alike. The population problem changes the scale because Magnetars may be born more often than once believed. That population forces a deeper look at hidden cases where surface clues no longer tell enough. Low-field Magnetars sharpen the paradox acting extreme even when their visible dipoles look surprisingly modest. Then Magnetar birth joins a larger chain linking stellar death-bright transients, mergers and recycled matter. The real birth is a hidden verdict on spin field growth fallback and survival inside collapse. Like, subscribe, and thank you for listening because our first step begins where the explosion misleads. The brightest part of a Magnetar's birth is also the most misleading. From a distance, the story looks simple. A giant star reaches the end of its life, detonates in a supernova, and leaves behind an exotic corpse. The sky flashes. The outer layers race away. Telescopes register a violent death. It feels like the explosion is the main event. But the real event is smaller than a planet, denser than anything the eye can imagine, and buried so deep inside the collapsing star that the light we notice is almost a distraction. A Magnetar is not born in the shining shell that announces the catastrophe to the universe. It is born in the hidden center, where a star stops being a furnace and becomes a trap for pressure spin and magnetic energy so extreme that ordinary language starts to fail. That is the first correction this story demands. The supernova is real. The brightness is real. The devastation is real. But the visible blast is only the surface expression of a deeper act of compression that happens when no one can look directly. What matters is not the explosion itself, but the verdict delivered in the core before the expanding debris has even begun to explain itself. That is why Magnetars remain so arresting. They seem to emerge from spectacle, yet their true origin is a hidden decision made under impossible conditions. To understand them, the familiar picture has to be inverted. The story on the surface is smaller than the story underneath. Start with the star before the light show begins. For millions of years, a massive star lives by maintaining a temporary settlement between gravity and fusion. Gravity presses inward with relentless patience. Fusion pushes outward with radiation, heat, and pressure. As long as hydrogen and later heavier fuels can keep releasing energy in the core, the star holds its shape. But this balance is not a permanent achievement, it is a lease. And near the end of a massive star's life, the lease runs out fast. The core begins burning heavier elements in shorter and shorter stages. The timetable that once ran on millions of years starts collapsing into centuries, then years, then days. The star looks enormous from the outside, but the machinery inside has become unstable. This is the second correction. Stellar death is not a single moment, it is a tightening sequence. The familiar image of a star exploding all at once hides the fact that the real crisis begins in the center, long before the outer layers know what is coming. Eventually the core becomes dominated by iron, and iron changes the argument. Earlier fusion stages have paid the star's bills by releasing energy. Iron does not. Iron is nuclear ash. Once the core reaches this dead end, the old contract between pressure and gravity fails in the most literal way possible. The support vanishes. Gravity does not hesitate. In a tiny fraction of time, the central regions plunge inward. A stellar lifetime is converted into seconds. Density rises catastrophically. Temperatures soar. Electrons are forced into protons. Matter is crushed toward a state it has no business occupying under normal conditions. The core does not simply shrink. It becomes a new regime of nature. And already the visible explosion, the thing most people imagine first, has been demoted. It has not happened yet. The decisive violence comes first in the dark. This is the part that matters for Magnetars, because not every core collapse produces the same remnant, and not every newborn neutron star becomes one of these magnetic monsters. Something more selective is happening in the wreckage. Something in those first seconds sorts ordinary survivors from exceptional ones. When the collapsing core reaches nuclear densities, the inward plunge cannot continue in the same way. The matter resists. The inner collapse halts and rebounds. A shock forms. Neutrinos flood outward. The outer layers, which have been falling inward behind the doomed core, are suddenly confronted with a violent reversal that helps drive the supernova blast we eventually see across galaxies. But even here the easy explanation fails. The explosion does not explain the Magnetar. It only announces that the star has crossed into a new state. At the centre, what remains is no longer a normal stellar core. It is a proto-neutron star, an object roughly city-sized, unimaginably dense, scorching, hot and newborn in the most dangerous sense of the word. Inside that object, conditions are still changing with ferocious speed. Matter churns, heat escapes in torrents of neutrinos, rotation tightens, magnetic structure is twisted, amplified and rearranged. The remnant has not settled into its final identity yet. It is still becoming itself. That unfinished interval is where the real question lives. Because a Magnetar is not merely a neutron star with more of everything. It is a neutron star that seems to cross a threshold. Its magnetic field becomes so strong that it can crack crust power intense X-ray flares and dominate the star's later behavior in ways ordinary pulsars do not. The difference is not cosmetic, it is structural, it is evolutionary, and it appears to be decided astonishingly early, when the remnant is still bathed in the chaos of its own birth. So the supernova is not the answer, it is the curtain. The object that matters is hiding behind it, compressed into a sphere barely tens of kilometers across, holding more mass than the sun, and carrying within it the possibility of one of the most extreme magnetic environments in the universe. To make such an object, a star must first fail at being a star, then survive collapse without becoming a black hole, then pass through a narrow corridor of conditions where heat density, angular momentum and magnetic amplification can combine into something far rarer than a normal remnant. That corridor is the real birthplace. And the closer we move toward it, the stranger the story becomes, because the next problem is not the explosion, not even the collapse, but why some newborn neutron stars emerge merely powerful, while a few are born armed with magnetic fields so immense that they rewrite what a stellar corpse can do. A Magnetar is not just a neutron star turned up louder. That is the next illusion this story has to destroy. Once the core of a massive star collapses, it is tempting to imagine that all neutron stars belong to the same family and differ only by degree, as if some are simply faster, hotter, or more dramatic than others. But Magnetars do not sit comfortably inside that easy picture. They behave like a branch that breaks away from the main line. They flare when quieter remnants do not. They unleash bursts of X-rays and gamma rays that make ordinary pulsars seem restrained. Their magnetic fields are so extreme that the field is no longer a feature of the star. It becomes one of the star's governing realities. This is the first tension of Section 2. A neutron star is already an outrageous object. It packs roughly stellar mass into something the size of a city. It bends light. It locks matter into states that cannot exist on Earth. It spins with terrifying speed. Yet even against that background, Magnetars still stand apart. The question is no longer how a star dies. The question is why a few of the survivors come out carrying a different kind of power. From the outside, both classes can be born from core collapse. Both are remnants of stars that fail in similar ways. Both can begin as ultra-dense stellar corpses formed in the violence after a supernova. But the similarity hides a divergence. A typical young neutron star may emerge as a pulsar radiating beams from its magnetic poles as it spins. Its field is strong by any ordinary standard, strong enough to dominate nearby plasma drive radiation and turn the object into a lighthouse sweeping through space. But a Magnetar lives in another regime. Its magnetic field can reach values so immense that the numbers stop feeling descriptive and start feeling abstract. The difference is not merely that the field is bigger. The difference is that the field becomes central to what the star is and how it evolves. A pulsar spins down, a magnetar disturbs itself, it stresses its own crust, it powers eruptions from stored magnetic energy. It turns hidden internal structure into observable violence. That is the real distinction. The magnetic field in a normal pulsar helps shape behavior. In a magnetar, it can dominate destiny. This is why the usual surface summary is too small. Calling a magnetar a highly magnetized neutron star is accurate but incomplete in the least satisfying way. It is like saying a volcano is a warm mountain. Technically true, narratively useless. What matters is the threshold. Somewhere in the birth process, the newborn remnant either remains inside the broader population of neutron stars or crosses into a condition where magnetism becomes the main internal engine of later activity. That threshold may depend on how fast the core is rotating, how violently the interior is convecting, how the field is amplified, how matter falls back after the explosion, or how the progenitor star was built long before collapse began. The visible remnant may look similar at first. The hidden inheritance may be radically different. This is the second correction. The difference between a pulsar and a magnetar is not simply a matter of appearance. It is a matter of formation history written into the object's interior, and that makes magnetars less like decorated neutron stars and more like a distinct verdict delivered during birth. The young neutron star is not born into peace. In its first moments it is still incandescent with leftover heat, still reorganizing under pressures so severe that matter itself is near the edge of known behavior. It can be convective, it can rotate rapidly, it can twist and redistribute magnetic structure on timescales short enough to matter for its final identity. These early seconds are not postscript, they are selection. If the conditions are ordinary enough, the remnant settles into a more familiar pulsar path. If the conditions are extreme enough, the remnant may emerge with a field strong enough to carry a different future. And once that future exists, the consequences ripple outward for years, centuries, and sometimes far longer. Magnetars can enter periods of apparent quiet, then suddenly release staggering bursts of energy. They can glow in X-rays more brightly than their rotation alone should permit. They can produce giant flares so violent that for a brief moment they announce themselves across enormous reaches of space. The obvious explanation is that they are simply more energetic neutron stars. The real explanation is more specific and more unsettling. They are objects whose magnetic configuration stores and releases energy at a scale capable of deforming the remnant itself. The star is not just spinning through the universe, it is wrestling with its own field. That is why magnetars force a more careful question. Not why neutron stars are strange. That answer is already too broad to be useful. The more exact question is why only a fraction of neutron stars appear to be born into this magnetic extremity. If core collapse is common on cosmic timescales, why is magnetar birth selective? If neutron stars are already born in violence, why do so few seem to emerge from that violence, carrying such disproportionate magnetic power? And if the difference is decided so early, then the remnant alone may not tell the whole story. We may have to look backward into the progenitor star and forward into the first seconds after collapse at the same time. This is where the narrative pressure increases. Magnetars are not interesting merely because they are rare. They're interesting because rarity implies conditions. Conditions imply mechanism. Mechanism implies a buried cause. Something about the dying star or the imploding core, or the way angular momentum and matter behave at the threshold of collapse is filtering outcomes. The supernova gives us a dead star. The deeper process decides what kind of dead star it will be, and that means the next layer of the story is no longer about what a magnetar does after birth. It is about the fatal sequence before and during collapse that creates the conditions for such a remnant at all, because the road to a magnetic monster does not begin with magnetism. It begins with the point at which fusion finally fails and iron ends the bargain that kept the star alive. The star does not die when it runs out of size. It dies when it runs out of favourable physics. That is the deeper turning point, and it arrives not at the surface, not in the expanding glow that later floods space, but in the core where fusion has been paying the star's bills for almost its entire life. A massive star looks powerful because it is powerful. It shines with such intensity that from far away it seems almost self-sustaining, as if brilliance were a kind of stability. But the truth is harsher. Stellar light is not proof of permanence, it is proof of expenditure. Every second the star is converting mass into energy using one finite reserve after another to hold gravity back. That is the bargain. Gravity presses inward without pause. Fusion pays for resistance. As long as the payments continue, the star remains a star. The moment they fail, the whole structure is exposed as temporary. This is what iron changes. It is not just another element in a sequence. It is the end of the sequence that matters for support. Earlier in the star's life, hydrogen fuses into helium, then in sufficiently massive stars, helium into carbon and oxygen, and later into heavier and heavier nuclei as the core contracts and heats, after each prior fuel source is exhausted. The process looks like progress only from a distance. In reality, it is a narrowing corridor. Each new stage burns hotter, faster, and for less time. Millions of years can be spent on hydrogen, far less on helium. Then the timetable begins to collapse. Carbon burning can last centuries, neon can be measured in years, oxygen can be consumed in months, silicon can vanish in days. The giant star still towers across space, but its inner clock is accelerating toward ruin. The obvious explanation is that the star dies because it has burned too much. The real explanation is more specific. It dies because the core eventually fills with ash that no longer yields energy by fusion. That ash is iron, and iron is the point where the old strategy stops working. The reason is unforgiving. Fusion releases energy only when lighter nuclei combine into configurations that are more tightly bound. Up to iron, the process can pay out. Beyond iron, the payment reverses. Trying to fuse iron does not liberate energy for support, it consumes it. At that point, the furnace at the center of the star is no longer a defense against collapse, it becomes a dead end. This is why iron is not merely the last step. It is the cancellation of the contract. The star may still look immense, its outer layers may still blaze, but the core, the part that matters most, has entered a state where its previous methods of survival are finished. And once the core is dominated by iron, the structure above it becomes a burden the center can no longer afford to carry. That burden is staggering. A massive star spends its whole life building weight above its core. Every fusion stage adds new layers, new shells, new pressure bearing down on the center. While energy is still being generated efficiently, that pressure can be answered. When iron takes over, the answer disappears. There is no negotiation left. No new reserve can be opened in time. No gentler equilibrium arrives to save the day. Gravity does what gravity has always wanted to do. It moves in. What follows is not slow decay. It is the collapse of delay itself. The core loses pressure support and plunges inward at catastrophic speed. Temperature climbs, but not in a way that rescues the star. Instead, the environment becomes so extreme that photons begin to work against the core by breaking apart heavy nuclei stealing energy that would otherwise oppose collapse. Electrons, which once helped provide degeneracy pressure, are captured by protons, creating neutrons and flooding the region with neutrinos. The matter changes character under the assault. The chemistry of ordinary life is gone. The architecture of atoms is gone. Familiar matter is being erased by compression. The deeper truth is that the star does not simply stop shining in the way a fire goes out. It undergoes a structural betrayal from within. The central support system converts from an engine into a liability. This is why the final stage feels so abrupt compared with the long grandeur that came before it. A massive star can spend millions of years creating the impression of stability and then fall apart in seconds once the physics of the core crosses the wrong threshold. Greatness does not save it. Scale does not save it. In fact, scale makes the ending worse. The more massive the star, the heavier the layers pressing down, the more terrible the collapse, when the core can no longer pay for resistance. And now the story tightens again because iron explains why collapse begins, but not why collapse sometimes leads to a magnetar instead of an ordinary neutron star or a black hole. Iron ends the bargain for every sufficiently massive progenitor that reaches this point. It does not by itself explain the rarer outcome, it only explains why the descent becomes unavoidable, yet that matters because magnetars are born inside that inevitability. They do not emerge from a healthy star, they emerge from a core whose old identity has been cancelled, whose support has failed, and whose matter is being driven into a regime where density, spin turbulence, and magnetic amplification can suddenly matter more than the quiet stellar history that came before. The long luminous life of the star narrows to a terminal experiment lasting moments. And inside those moments, the central question changes. It is no longer whether the star can survive as a star. It cannot. The real question is what kind of remnant that collapsing core can still become before the catastrophe finishes unfolding, because once iron ends the bargain, the next step is not death in the abstract. It is compression so violent that the imploding center begins creating the exact conditions from which a magnetar may be born. The collapse does not merely destroy the star, it manufactures the conditions for a different kind of object to exist. That is the point where this story becomes more than a death sequence. If Section 3 is where the old order fails, Section 4 is where a new and far stranger order begins to assemble under violence so intense that the distinction between ending and creation almost disappears. A massive star's core once iron has ended, the old bargain falls inward with a speed and seriousness that ordinary collapse cannot capture. This is not sagging, settling, or imploding in the casual sense. It is a plunge in which matter is driven past the limits of normal compression and into a regime where the structure of atoms no longer survives as a meaningful description. The star has stopped being an engine and has become a compression machine. What matters now is not the outer star that still exists for a few last moments above the disaster. What matters is the center where density rises so fast that nature is forced to reveal new rules. The obvious explanation is that collapse simply crushes the core until a compact remnant is left behind. The real explanation is more dynamic and more violent. As the inward fall accelerates, the core heats catastrophically, but that heat does not reverse the process in time. Instead, particles are driven into new relationships. Electrons are forced into protons through capture processes that produce neutrons and neutrinos. The free room inside atoms disappears. Matter becomes less like a collection of nuclei and electrons, and more like a packed continuum of nuclear-scale resistance. The collapse is rewriting the material identity of the star from the inside out. This is why neutron stars are not merely dense leftovers. They are objects forged when gravity pushes matter into a state that resembles an enormous atomic nucleus. But even that description is too calm for the birth moment itself. The remnant is not born quietly into equilibrium. It is born incandescent, unstable, convective, and still fighting the aftermath of its own creation. Before it becomes a neutron star, in the settled sense it exists as a proto-neutron star, and that prefix matters more than it sounds. Proto means unfinished. Proto means still deciding what kind of remnant it will be. Proto means the collapse has produced the raw object, but not yet the full verdict. At the heart of the implosion, once nuclear densities are reached, matter finally pushes back hard enough to halt the inner collapse. This is not a triumph. It is a temporary refusal to become something worse. The inward plunge of the central region arrests abruptly, and the sudden stiffening creates a rebound. A shock forms and begins moving outward. Around it, the rest of the star is still falling in. Neutrinos flood from the infant remnant in staggering numbers, carrying away energy and altering conditions throughout the surrounding matter. The inner star has become an arena of opposing catastrophes, in full rebound, heating, neutrino escape, and shock propagation, all entangled on timescales that are brutally short. This is the deeper reality behind the familiar word supernova. The explosion people imagine is not a single clean blast. It is the outward expression of a central crisis in which collapse, bounce, and neutrino-driven processes struggle to decide how much of the star will be expelled and what will remain. And in the middle of that unresolved violence sits the proto-neutron star, still hot enough to churn, still compacting, still reorganizing its interior. That is the first truly fertile environment for Magnetar birth. Not because the Magnetar is already fully there, but because the collapse has finally created the ingredients from which such an object might emerge. The remnant is now small enough, dense enough, and energetic enough for rotation turbulence and magnetic structure to interact on extraordinary terms. Angular momentum that once belonged to a vast stellar core is being concentrated into a much smaller body. Any magnetic field threaded through the collapsing matter is being compressed and intensified. Convection can drive movement through the newborn remnant in ways that matter profoundly for later amplification. The object is not stable in the ordinary sense. It is a furnace of reorganization. This is why the collapse matters so much. It does not give us the Magnetar in finished form, but it builds the stage on which the decisive amplification can occur. Without collapse, there is no proto-neutron star. Without the proto-neutron star, there is no interval in which the remnant's early heat spin and internal motion can produce a radically different magnetic future. The story on the surface is still lagging behind. Even as the supernova shock works outward and the star begins to tear itself apart, the real transformation remains hidden inside the compact object that the collapse has just produced. What we are watching from afar is a bright announcement of destruction. What is actually happening at the centre is a selection process among remnants. Some newborn cores will settle into more ordinary neutron stars. Some will collapse further into black holes, either promptly or after a brief unstable survival. And a smaller number may enter the narrow corridor where the field is amplified, organized, buried, twisted, or regenerated into Magnetar strength. The collapse, in other words, does not answer the question by itself, but it creates the only environment in which the answer can be made. It compresses matter into nuclear densities. It creates the proto-neutron star. It concentrates spin. It intensifies inherited magnetic structure. It unleashes neutrino-driven convection and violent internal motion. It shrinks the problem from the scale of a star to the scale of a city without reducing the mass enough to make the situation manageable. The achievement is real. The cost is larger. A star has to be broken almost beyond recognition before a Magnetar can even become possible. And now the pressure of the story moves forward again, because once the proto-neutron star exists, the decisive question is no longer whether collapse can create the right kind of object. It is whether the first seconds of that object's life are extreme enough to turn possibility into destiny. A Magnetar may be decided before the supernova has even finished explaining itself. That is the next reversal. It feels natural to imagine that the star's long life should matter most, that millions of years of mass-loss fusion history and stellar structure must outweigh whatever happens in the brief chaos after collapse. But the birth of a magnetar appears to depend with brutal sensitivity on a much shorter window. Seconds, not ages, not eras. Seconds in which the newborn remnant is still a proto-neutron star, still hotter than almost any ordinary comparison allows, still flooded by escaping neutrinos, still convecting, still rotating, still reorganizing its interior, faster than the expanding debris outside can reveal what has happened. The obvious explanation is that the remnant simply inherits its identity from the progenitor. The real explanation is harsher and more selective. Inheritance matters, but the first moments after collapse may matter more. They do not merely decorate the remnant. They decide whether the object settles into a more familiar neutron star life or crosses into magnetic extremity. This is what makes the earliest phase so important. The proto-neutron star is not born finished. It is born overpressured, incandescent and unstable. Its interior temperature is enormous. Neutrinos produced in staggering quantities are trying to escape, and in doing so carry away a tremendous amount of energy. Matter is so dense that even these elusive particles do not leave instantly. They diffuse outward through the remnant and help drive the object's thermal evolution on timescales that are astonishingly short by stellar standards. At the same time, the newborn core may be convective with hot matter, rising and cooler matter sinking in violent circulation. Rotation, if fast enough, can impose order on some of that chaos, while also generating new instabilities of its own. Differential rotation can make one layer turn faster than another. Shear can stretch and wind magnetic field lines. Turbulent motion can tangle them, amplify them or redistribute them. The object is not just cooling, it is processing its own future. This is why the first seconds are not aftermath. They are assembly. A star spends millions of years becoming vulnerable to collapse, but the compact remnant that emerges may reveal its deeper identity in a tiny fraction of that time. The scale is almost offensive to intuition. So much stellar history narrowed to an interval short enough to count. And yet, this is precisely where the Magnetar question sharpens, because magnetic fields are not passive in this environment. They can be compressed by collapse, but compression alone may not be enough to explain the most extreme cases. The deeper possibility is that the early remnant acts as a magnetic amplifier. If the proto-neutron star is spinning fast enough, and if its interior motion remains vigorous enough, then a dynamo-like process may drive the field to strengths that an ordinary pulsar never reaches. This is one of the most compelling ideas in Magnetar birth, not that the field is merely preserved, but that it is built upward during the remnant's first living moments as a compact object. That makes the birth process feel less like inheritance, and more like ignition. But here the story becomes narrower, because not every proto-neutron star can do this. The conditions are demanding. The remnant may need to rotate extremely rapidly, perhaps on millisecond timescales. It may need the right combination of convection, shear and survival time before fallback, or further collapse changes the picture. It may need to avoid becoming a black hole too quickly. A slight difference in spin mass distribution or internal transport could push the outcome toward an ordinary neutron star, a magnetar, or something that never stabilizes long enough to matter. This only looks simple from a distance. Up close, the first seconds are a selection regime where multiple thresholds are being crossed at once. The remnant must cool, but not too quickly, to erase the activity that amplifies the field. It must rotate fast, but not in a way that immediately guarantees deeper instability. It must survive the birth process without prompt collapse. It must allow internal motions to act before the structure settles. That is why Magnetar birth can feel less like a standard product of core collapse, and more like a narrow victory won inside a storm of competing timescales. The achievement is real. The margin may be small. And even that may understate the difficulty, because the field that ultimately matters may not be only the dipole field an observer infers much later. Some of the most important magnetic energy may be stored in internal toroidal structure tangle configurations, or buried components that do not immediately declare themselves at the surface. In other words, the remnant may already be becoming a Magnetar before the sky has clear permission to call it one. The visible aftermath can lag the internal truth. That is a recurring rule in this story. The surface explanation comes second, the hidden process comes first, and once that is understood, the first seconds become more than a technical detail. They become the decisive theatre in which the remnant's entire future is being negotiated. Will it become a pulsar whose spin powers most of what we later observe? Will it become a magnetar whose magnetic stress can crack crust drive flares and dominate the long afterlife of the object? Or will the newborn core fail to remain a neutron star at all? Those are not late questions. They are early ones. They belong to the remnant while it is still cooling through neutrinos and still convulsing with internal motion, which means the next layer of the story is even more exacting, because once the first seconds are recognized as decisive, the problem tightens to a harder question. Still, what specific ingredient within that window gives a newborn remnant the power to amplify its field into the Magnetar range? And why does rapid rotation appear to sit so close to the center of that answer? A newborn neutron star can spin so fast that an entire city-sized object turns in a few thousandths of a second, and that speed is not ornament. It is power in one of its rawest forms. This is where the Magnetar story stops being merely a story about survival after collapse and becomes a story about conversion. Because rapid rotation does not just make the remnant look dramatic, it changes what the remnant can do to itself. The easy explanation is that the magnetic field of a Magnetar is simply inherited from the star that died. Collapse shrinks the core, the field is compressed, the numbers become enormous, and the case is closed. But that explanation is too neat for an object this extreme. Compression matters. Inheritance matters. Yet the stronger possibility is that a fast newborn remnant can actively build a much more powerful field during its first moments as a proto-neutron star. In that picture, spin is not an afterthought. Spin is fuel for magnetic amplification. To see why, the scale has to be felt properly. Before collapse, the stellar core may already be rotating, though usually not at a pace that sounds extraordinary on human terms. But collapse changes scale with merciless efficiency. Angular momentum conserved as the core contracts from something thousands of kilometers across to something only tens of kilometers wide drives the remnant to much faster rotation. It is the familiar figure skater analogy, but with far higher stakes. Pull mass inward, and the turning accelerates. What had once been spread across a large core is now concentrated into an object roughly the size of a city, but carrying the mass of a star. The result can be breathtakingly fast spin, especially if the progenitor has retained enough angular momentum before collapse. And once that speed exists, the interior of the newborn remnant stops being a passive container. It becomes a machine for winding, stretching, and reorganizing magnetic structure. This is the first important correction. A magnetic field is not a static label attached to matter. In a conducting fluid or plasma, motion and field interact. Move the fluid, and the field can be dragged, twisted, amplified, or reconfigured. The proto-neutron star is exactly the kind of object in which such interactions matter. Hot, conductive, convective, rapidly rotating and violently out of equilibrium. Differential rotation means different layers or regions may spin at different rates. That shear can wind poloidal field into toroidal field wrapping lines around the star and intensifying them. Convection can churn and recycle magnetic structure, potentially enabling dynamo action that pushes the field far beyond what simple compression alone would provide. The remnant is not merely conserving a magnetic inheritance, it may be upgrading it under pressure. That is why rapid rotation sits so close to the center of one of the leading Magnetar formation ideas. If the proto-neutron star is rotating on millisecond timescales, then the available rotational energy is enormous. Not abstractly enormous, mechanically enormous. Enough to affect internal transport, enough to organize turbulence, enough to feed amplification processes that can drive the field into the Magnetar range. The star's collapse has already created density and heat. fast rotation may provide the missing leverage that turns those conditions into a magnetic engine. Without it, the remnant may still become a neutron star with a strong field. With it, the remnant may cross into another category altogether. But here the story sharpens again because speed by itself is not a guarantee. This only looks simple from a distance. One could imagine a universal rule spin fast become a Magnetar. Yet the evidence and the theory both resist such clean reduction. The remnant still has to survive long enough for amplification to matter. It still has to manage neutrino cooling convection and internal instabilities. The progenitor's prior structure still shapes how much angular momentum is available in the collapsing core. Magnetic braking earlier in stellar life may have already reduced that budget. Binary interactions may alter it. Internal transport during stellar evolution may redistribute it. In other words, rapid rotation may be necessary in some pathways, but it does not act alone. It acts inside a crowded argument involving mass structure, transport and time. Even so, the logic of why spin matters remains powerful. Rotational energy is one of the few truly vast reservoirs available in the newborn remnant. A Magnetar's later activity requires stored energy capable of stressing the crust, powering bursts and shaping long-term evolution. A fast spin at birth offers a plausible route to building at least part of that reservoir by amplifying magnetic structure when the remnant is young enough and dynamic enough for the process to work. The obvious explanation is that Magnetars are defined by field strength. The deeper explanation is that field strength itself may be the fossil record of a much earlier struggle over rotational energy. In that sense, the magnetic monster seen later is the afterimage of an argument won in the first seconds, and that has consequences beyond the remnant itself. If a newborn neutron star is born spinning rapidly enough and carrying an extreme field, it may also inject additional energy into the surrounding explosion, alter the appearance of the transient or help power, unusually luminous events. The remnant is not just inheriting a corpse, it may be changing the visible aftermath of the star's death. That widens the scale of the problem. Rapid rotation is not just important because it may help explain Magnetars. It may help connect the hidden birth physics of the compact object to the brightness and behavior of the explosion outside, but the story still refuses to become too clean. Some Magnetars may not require the most extreme initial spin. Some may form through other routes. Some may hide their internal field in ways that make the surface look less exceptional than the buried energy really is. And some neutron stars that begin fast may fail to keep the conditions needed for the full transformation. That is why rapid rotation is best understood not as a decorative extra, nor even as a universal answer, but as a powerful and plausible engine inside one major pathway to Magnetar birth. It is the difference between merely being compact and being able to build magnetic violence from within. Yet even that may not rescue every candidate, because a remnant born without the ideal spin may still receive a second darker opportunity when matter from the failed explosion starts falling back toward the core. The explosion does not always get the last word. That is the next complication, and it matters because one of the most important ingredients in Magnetar birth may arrive not during the cleanest part of the core collapse, but during the mess that follows, when the dying star fails to throw all of itself away. The familiar supernova picture suggests a decisive event. The core collapses, the shock moves outward, the star is blasted apart, and what remains at the center begins its afterlife in relative isolation. But this only looks orderly from a great distance. In reality, the aftermath can be unstable, asymmetrical and unfinished. Some of the matter that the explosion tries to expel does not escape for good. It slows, it stalls, it turns around, and then it falls back toward the compact remnant that has only just been born. This is fallback, and it changes the story because it means the newborn neutron star may not simply inherit its future from the moment of collapse alone. It may be rewritten by material returning from the failed edges of the explosion. The obvious explanation is that fallback is just leftover debris cleaning itself up. The real explanation is more dangerous. Returning matter carries mass angular momentum and pressure. It can load the remnant with new weight. It can alter its spin. It can bury magnetic structure beneath freshly accreted material. It can push a marginal survivor over the line into black hole formation. Or under the right conditions, it can give a slower or less extreme newborn neutron star a second path toward Magnetar birth. That is why fallback matters so much. It is not an afterthought. It is a second round of selection imposed after the first. The collapsing core may produce a proto-neutron star that is promising but not yet decisive, a remnant, whose rotation is significant but not yet ideal, whose field is strong but not yet dominant, whose survival is real but not yet guaranteed. Then the surrounding explosion begins to fail in patches. Reverse shocks can form in the expanding ejector. Material launched outward can lose energy and rain back inward. Over seconds, minutes, hours, or longer, depending on the structure of the star and the explosion, the newborn remnant may begin swallowing part of the star it thought it had already escaped. This is where the easy story breaks apart. Supernovae are not always clean severances. Sometimes the dead star keeps trying to reclaim its own center, and if enough matter returns, the consequences become profound. Accreting material can transfer angular momentum to the remnant. In plain terms, fallback can spin the object up. A neutron star that did not begin life rotating at the most extreme rates may be driven faster by what comes back down. Under some models, that means fallback is not merely a threat, but a possible rescue for Magnetar formation. The remnant may miss the ideal dynamo conditions at first and still acquire them shortly afterward, through renewed accretion and internal readjustment. The star fails, the explosion fails to clear everything, and that second failure creates a new opportunity. The achievement is real. The route is uglier. This is one of the most revealing patterns in the Magnetar story. The universe does not always produce extremes through clean, elegant channels. Sometimes it uses disorder, delay, and partial failure to arrive at a more violent outcome. But fallback is double-edged. The more matter returns, the more dangerous the remnant situation becomes. Additional mass can deepen gravity's claim on the center. A newborn neutron star exists near one of nature's most brutal thresholds. Add too much weight, or add it too quickly, and the remnant may no longer be able to support itself, even in neutron star form. In that case, the second chance becomes a death sentence. The compact object collapses further and becomes a black hole. So fallback creates a narrow corridor. Too little, and it may not matter much. Too much, and the remnant is erased. Somewhere in between, it may amplify rotation effect field growth or help set the stage for Magnetar behavior. That makes the process especially important for explaining why the same broad class of stellar deaths can produce such different endpoints. A core collapse supernova is not a single deterministic machine that stamps out identical remnants. It is a branching event in which late-in-fall internal transport and survival thresholds can all alter the outcome. Fallback also complicates the magnetic story in another way. If substantial material accretes onto the newborn neutron star, it can bury the external field beneath the outer layers. This means the remnant's true magnetic violence may not immediately be visible at the surface. The field can be intense yet hidden. The dipole inferred by a later observer may understate what the object is really carrying inside. That is crucial because it helps explain how some neutron stars may behave like Magnetars without advertising the most extreme surface field from the start. The visible appearance can lag the deeper truth again. The object is born into one magnetic condition, then covered distorted or delayed by the very matter that failed to escape. Over time, some of that buried field may diffuse back outward, changing the remnant's observed character long after the birth process itself. In this sense, fallback does not simply add matter. It interferes with diagnosis. It can make Magnetar birth look simpler or stranger than it really was, depending on when the object is observed. And that widens the meaning of the problem. We are not just asking how Magnetars are made, we're asking how often their real birth signatures are masked by the ugliness of the explosion that surrounds them. This is why fallback deserves to be treated not as a technical footnote, but as one of the story's darker pivots. It turns supernovae from single-step endings into layered negotiations. It gives the remnant another chance to gain rotational leverage. It threatens that same remnant with obliteration. It can bury the field that later defines the object. It can make an apparently ordinary neutron star into a delayed Magnetar candidate, or collapse a would-be candidate into a black hole before the field can matter at all. The story on the surface is smaller than the story underneath, and fallback makes that painfully literal, because the matter that fails to escape the star may become part of the reason a Magnetar exists. But the deeper implication is even more unsettling. If fallback can rescue some births, mask others, and erase many outright, then there may be no single clean mechanism behind all Magnetars. The pathway may already be splitting, and the next question is whether Magnetars are born through one dominant recipe, or through several competing channels that all converge on the same terrifying kind of remnant. The most dangerous mistake now would be to think there must be only one way to make a Magnetar. That is the kind of simplification the story keeps punishing. Once rapid rotation enters the picture, it is tempting to lock onto a single dramatic mechanism. A massive star collapses, its core spins at millisecond speed. A powerful dynamo amplifies the magnetic field, and the remnant emerges as a Magnetar. It is clean. It is elegant. It feels like the sort of answer nature should prefer, but nature is rarely obliged to choose the cleanest explanation when several messier ones can survive. And Magnetars, precisely because they sit at the crossroads of extreme magnetic fields, supernova violence fallback, and compact object survival, may be the product of more than one birth channel. The obvious explanation is that all Magnetars are the same kind of object, and therefore must come from the same kind of formation. The real explanation may be more unsettling. Similar outcomes can be reached by different routes, and the compact remnant we later call a Magnetar may be the common endpoint of several distinct histories. That matters because it changes the kind of question being asked. Instead of searching for one perfect recipe, the problem becomes identifying a family of conditions that can all converge on the same magnetic extremity. The most famous pathway remains the rapid rotation dynamo picture. In that version, the newborn proto-neutron star is born spinning fast enough and remains active enough internally for convection and differential rotation to amplify the field to Magnetar strength during the first seconds. It is still one of the strongest candidates because it explains why birth conditions matter so much, and why some of the brightest stellar deaths might be linked to Magnetar engines. But it is not the only serious possibility. There is another idea, older in spirit and quieter in presentation, that begins before the collapse itself. In that picture, the progenitor star may already carry an unusually strong magnetic field long before it dies. The Magnetar's violence would then be at least in part the compressed inheritance of a highly magnetized stellar core. Collapse would intensify what was already there. The remnant would not need to build everything from scratch if the progenitor had entered death, carrying an exceptional fossil field. This pathway is attractive because stars are not magnetically identical during life, and some massive stars do appear to host strong surface and internal fields. Yet the explanation is not complete by itself, because even a fossil field has to survive stellar evolutions, internal mixing, possible mass loss, and the brutal rearrangements of collapse. The inheritance model is plausible. The question is whether inheritance alone is enough. Then there are pathways made stranger by companionship. A massive star does not always live alone. In binary stars can mass trade angular momentum strip one another's envelopes or merge outright. And mergers matter because they can create progenitors, unlike the isolated stars that simpler narratives assume. A merger can spin up the core. It can alter internal structure. It can preserve or intensify magnetic complexity. It can leave behind a star whose final collapse is not the ordinary death of a single star at all, but the delayed consequence of two histories being forced together into one body. This is one of the most revealing enlargements of the Magnetar story. The remnant may look singular. The cause may have been collective. By the time the star dies, it may already be carrying the hidden consequences of an earlier stellar collision or mass transfer episode that primed the core for a more extreme collapse. In that sense, some Magnetars may be born in the supernova, but prepared in the binary, And still, the branching continues. Fallback, as already seen, offers yet another route. A remnant that is not born under the ideal fastest spin conditions may still accrete enough returning material to alter its angular momentum, bury, and later reveal magnetic structure, or pass through a delayed phase of field growth and magnetic dominance. Here the Magnetar is not the product of a single explosive instant, but of a two-step birth, in which collapse creates the remnant and failed ejection modifies it afterward. The Magnetar emerges from a death that could not finish cleanly. The achievement is real. The causality is split. These competing channels do not cancel one another. They may coexist. That is what makes this section so important. Magnetars may form through different combinations of pre-collapse structure rotation, binarity, magnetic inheritance fallback, and survival thresholds, all of which can vary from one progenitor to another. Two remnants may both end up classified as Magnetars while carrying very different internal histories. One may be the child of rapid dynamo amplification. Another may be the compressed air of a strongly magnetized progenitor. Another may owe its existence to merger-driven spin-up. Another may have had its field buried and reshaped by fallback before becoming recognizable. From the outside, the category appears singular. Underneath it may be assembled from multiple roads. This only looks like disorder if one expects nature to prefer tidy bookkeeping. In reality, what matters is not that every Magnetar is born the same way. What matters is that several pathways may be able to cross the same threshold, a remnant whose magnetic energy becomes large enough, structured enough, and durable enough to dominate the object's later behavior. The event itself may vary. The system beneath it may not. That is the deeper unifying idea. The road can change. The destination remains magnetic rule, and that realization changes how the evidence must be read. A single observational clue is unlikely to settle the whole formation problem. Different progenitors may leave different supernova remnants, different companion histories, different birth spins, different fallback signatures, and different external field appearances. If Magnetars are a mixed population, then disagreement in the evidence is not just noise. It may be the signal of multiple channels overlapping, which means the next step in the descent is unavoidable, because once a category may hide several different birth routes, the measured surface field alone becomes a dangerously incomplete guide. The remnant can look one way from the outside and be carrying something far more powerful beneath. The magnetic field we measure is not necessarily the magnetic field that matters most. That is one of the most important and least intuitive corrections in the entire Magnetar story, because once a remnant can no longer be treated as a simple dipole, with a neat external geometry, the numbers that seem most definitive begin to lose some of their authority. A Magnetar is usually introduced through field strength. The description is irresistible, a neutron star with a magnetic field so immense that it can dominate the object's behavior power, violent bursts and rank among the most extreme environments in the universe. But even this description can mislead if it suggests that the field inferred from spin-down or surface behavior is the whole truth. It may be only the visible fraction of a deeper magnetic architecture, and in some cases not even the most important fraction. The obvious explanation is that if a neutron star's measured dipole field is lower, then its Magnetar nature must be weaker or doubtful. The real explanation is more dangerous. The external field you can estimate may be only the outer signature of an interior carrying far more magnetic energy than the surface reveals. This matters because Magnetars are not defined merely by what they display to distant observers. They are defined by what their magnetic structure does to the star itself. A neutron star is not a rigid magnet floating unchanged through space. It is an ultra-dense object with a crust, a fluid or superfluid interior, extreme conductivity and magnetic stresses that can build over time as the field evolves, decays, reconfigures or pushes against the matter that contains it. In that setting, the geometry of the field matters as much as the headline number. A strong dipole field extending into space is one thing. A powerful internal toroidal field wound through the stellar interior is another. Tangled or multipolar components near the crust are another again. These different pieces do not announce themselves equally. Some are easier to infer from timing behavior. Some leave stronger marks in outbursts. Some may hide beneath the surface for years while still storing enormous amounts of energy. That is why the Magnetar story keeps escaping any attempt to flatten it into a single measurement. The field you see may not be the field that is driving the star toward eruption. This becomes clearer once the crust enters the story. A Magnetar's crust is not weak in any ordinary sense. In fact, neutron star crustal matter is among the most formidable material configurations known in nature. But even extraordinary strength is relative. If internal magnetic stresses become large enough, or evolve in a way that drags against the crust's ability to hold shape, the crust can crack, shift, or yield. When that happens, energy stored in the magnetic field can be released through bursts, flares and radiative episodes that far exceed what rotation alone can power. That is one of the strongest clues that the deeper engine is not just surface magnetism in the simplest sense. Something more is loaded inside the star, something that can stress it from within. The visible dipole may explain part of the remnant's braking and spin evolution, but the violent behavior may be tracing hidden components that are harder to see directly and harder to summarize cleanly. This is where the earlier sections begin to converge. Rapid birth rotation dynamo amplification, fossil inheritance fallback burial, and multiple formation channels all point toward the same conclusion. The observed surface field may be an incomplete record of a more complicated magnetic history. A remnant may be born with a field that is amplified and then redistributed. It may have strong toroidal components trapped inside. It may experience fallback that buries part of the external field beneath newly accreted matter. It may later re-emerge in a form that changes the apparent identity of the object. In such cases, a neutron star could behave like a magnetar, even if the dipole field inferred at the surface does not look extreme enough to satisfy the older stereotype. This is why low-field magnetars are so important conceptually. They do not merely add a curious subclass. They attack the assumption that the observable dipole is the final judge. They suggest that magnetic violence can persist even when the most familiar external estimate appears modest. The answer seems clear until the scale becomes visible. Once the interior is allowed to matter, surface simplicity stops being trustworthy. And that raises a more unsettling possibility. Some neutron stars, classified outside the traditional Magnetar category, may be carrying hidden magnetic reservoirs large enough to produce Magnetar-like episodes under the right conditions. The categories themselves may be cleaner than the objects deserve. A pulsar, a high-field pulsar, a transient magnetar, a low-field magnetar. These labels help observers organize behavior, but nature may be operating on a deeper continuum of buried energy, field geometry, crustal stress, and evolutionary timing. The remnant does not care what it is called. It only responds to the balance between the field it contains and the matter trying to hold that field in place. This only looks like a classification problem. It is really a structural problem. What kind of magnetic configuration survives birth? What becomes buried? What diffuses back out? What twists inside the crust before the crust can no longer bear it? Those are the questions that matter if one wants to understand why some objects erupt, why some appear quiet before bursting into activity, and why the same broad family of compact remnants can display such different behavior over time. The visible field is part of the truth. The internal field may be the part that decides the future. That is the larger reframe. Magnetars are not just strong magnets in space. They are stars whose magnetic interiors store enough energy and tension to deform the object's own life from within. And once that is understood, the next step in the story becomes unavoidable. Because if the most important magnetic reality is partly hidden, then the birth of a magnetar should not be judged only by what the remnant is. It should also be judged by what the remnant leaves behind, disturbs around itself, and writes into the surrounding sky after the explosion is over. A magnetar does not stay hidden forever. That is the next turn, and it matters because for all the secrecy of its birth, the object eventually begins writing evidence into the world around it. Not perfect evidence, not a clean confession, but scars, clues, disturbances that tell us the compact remnant at the center of a dead star may be something more extreme than an ordinary neutron star. The previous section moved inward toward buried magnetic architecture and hidden reservoirs of stress. This section has to move outward again because magnetars are not merely defined by what they contain. They're also defined by what they do after birth to the sky around them. The obvious explanation is that once the supernova is over, the story fragments into separate pieces, a compact remnant here, an expanding shell, the radiation later, maybe a remnant nebula, if observers are fortunate. But the real explanation is more connected. The compact object and the aftermath remain entangled. A magnetar can leave fingerprints in its supernova remnant in the chemistry and geometry of the expelled matter, in the radiation released years later, and sometimes even in the motion of surviving companions or the asymmetries of the blast itself. The birth is hidden, but it is not silent. Start with the most immediate consequence. A magnetar is born inside a supernova remnant, the expanding debris field of the star it used to be. That remnant is not just rubble, it is an archive. Its size, shape, age, energy, and composition can all carry information about the explosion that created the compact object at the center. If the newborn remnant injects additional energy into the explosion through rapid spin-down or magnetic activity, then the supernova ejector may expand differently than a simpler explosion model would predict. If the collapse is asymmetric, the compact object may receive a kick, sending it moving through or away from the remnant with startling speed. If the progenitor star lived in a binary or interacted strongly before death, the surrounding environment may already be structured by earlier wind-stripped material or companion influence before the explosion ever begins. In other words, the remnant is not background scenery, it is part of the evidence. That evidence, however, is frustratingly incomplete. Supernova remnants evolve. They expand, cool, mix, collide with surrounding gas, and erase some of the sharper features of their youth. The compact object at the center may also change faster than the remnant as entering active phases, quieter phases, or transient episodes that complicate the attempt to connect present behavior to birth conditions. This only looks like a straightforward forensic problem. In reality, Magnetar archaeology is an argument with time. The object we observe may be thousands of years removed from its most decisive formation moments, and the debris around it may already have been reshaped by interactions the original explosion never intended. Even so, Magnetars remain unusually revealing, because their later behavior can be so difficult to explain with ordinary rotational energy alone. A typical pulsar can power much of its activity through spin-down. A magnetar often looks different. It can emit X-rays too intensely for its rotation to reasonably sustain. It can produce bursts and flares that suggest internal magnetic stress is being suddenly released. It can show long intervals of relative quiet followed by abrupt radiative awakening. These are not generic leftovers of stellar death. They are signs that the compact object is still converting hidden energy into observable disturbance. That changes the meaning of the aftermath. The explosion is over, yet the remnant keeps behaving as if a piece of the original crisis remains unresolved. And in a sense, it does. The magnetic field built or intensified during birth continues evolving afterward, stressing the cross-driving emission, and sometimes reconfiguring itself violently enough to produce giant flares. These later episodes are among the most dramatic signatures Magnetars offer. A flare can release extraordinary amounts of energy in a tiny interval, briefly making the object one of the most luminous high-energy sources in its environment. Such events do more than confirm that the remnant is unusual. They reveal that the deeper engine remains active long after the star has died. The field is not a relic. It is a living source of consequence. There are broader scars as well. In some cases, the supernova environment may hint that the progenitor was unusually massive, unusually stripped or shaped by binary history. A surviving companion, if present, may be moving away at abnormal speed, carrying the kinematic memory of the explosion that destroyed its partner. The ejector may be enriched in ways that reflect the internal burning history of the star before collapse. the compact object itself may sit off-center, within the remnant evidence of a natal kick launched during the asymmetry of the explosion. None of these clues alone proves Magnetar birth, but together they widen the frame. A Magnetar is not just an object, it is the center of a disrupted system whose pieces may still be testifying long after the core collapse has ended. This is why observational astronomy keeps returning to Magnetar environments. The remnant, the surrounding gas, the timing behavior, the burst history, the spatial motion, and the larger stellar neighborhood all help reconstruct a formation story that the birth flash itself did not clearly explain. The answer seems clear until the system becomes visible. Once the full environment is included, the compact remnant stops being an isolated mystery and becomes a node in a chain of evidence extending backward to the progenitor and outward to the explosion debris. The hidden field inside the star leaves outward marks in radiation motion and structure. That is the deeper lesson of Section 10. A magnetar's birth is concealed, but its consequences are not fully containable. They spill into the sky around it. They disturb the remnant. They reappear in bursts. They turn the aftermath of a stellar death into a long forensic argument between hidden origin and visible consequence. And once that connection is accepted, the next layer becomes even larger, because if a newborn Magnetar can continue injecting energy and magnetic violence into the aftermath of stellar collapse, then some of the brightest and strangest explosions in the universe may not merely produce Magnetars, they may actually depend on them. Some of the brightest explosions in the universe may be impossible to explain cleanly, without newborn Magnetar hiding inside them. That is where the story stops being merely about one exotic remnant, and starts reaching into the architecture of the most extreme stellar deaths themselves. A supernova is already a vast release of energy. It tears apart a star drive's debris across space at thousands of kilometers per second, and can briefly rival the light of entire galaxies. By any ordinary standard, that should be enough. Yet astronomy keeps finding explosions that refuse to remain ordinary. Some supernovae shine too brightly for too long. Some transients rise and fade with a persistence that strains simpler models. Some gamma-ray burst afterglows display plateaus or power sources that seem oddly sustained, as if the catastrophe has found a hidden battery it should not possess. The obvious explanation is that the explosion was simply bigger, the progenitor more massive, the radioactive debris more abundant. Sometimes that works, often it does not. The real problem is not brightness alone. It is the endurance of brightness, the timing of the emission, and the amount of additional energy the visible event appears to require after the first blast should already be spending itself. This is where Magnetars enter not as curiosities at the edge of the story, but as serious engine candidates at its center. Imagine the birth of a neutron star that does not merely survive collapse, but emerges spinning with extraordinary speed and carrying an enormous magnetic field. Such an object contains a staggering reservoir of rotational energy. If that energy is shed on the right timescale through magnetic braking and interaction with the surrounding ejector, then the compact remnant can keep feeding power into the explosion after the initial core collapse has already occurred. In that picture, the supernova is no longer just a release, it becomes a coupled system. The outer star explodes, yes, but the compact object left at the center continues doing work. The remnant acts like an engine embedded in the wreckage, converting its own spin and magnetic structure into additional luminosity. That is one of the most compelling reasons Magnetars matter beyond their own immediate identity. They may help explain why some stellar explosions look as though they refuse to fade on schedule. This does not mean every unusually bright supernova must contain a Magnetar. That would be the same simplifying mistake the story has punished all along. Some events may be powered by interaction between ejector and dense circumstellar material shed before the star died. Some may involve unusually large yields of radioactive nickel. Some may belong to categories where black hole accretion jets or other central engine behavior plays a decisive role. But the Magnetar hypothesis remains powerful because it links several otherwise awkward facts into a coherent internal logic. A rapidly spinning newborn Magnetar has the energy, A strong magnetic field provides the mechanism for losing that energy quickly enough to matter. The expanding ejector provides the medium through which that input can be thermalized and re-radiated. The result is not just a brighter explosion, it is an explosion whose light curve duration and evolution may carry the signature of a compact object still injecting power after birth. In other words, some supernovae may be telling two stories at once. On the surface, they tell the story of a star dying. Underneath, they may also be telling the story of a magnetar spinning down inside the debris. This is especially important for the class of events often called superluminous supernovae explosions, so bright that ordinary core collapse expectations struggle to explain them cleanly. The name itself already signals the problem. These are not merely strong explosions, they are explosions whose brilliance forces a deeper question about continuing energy supply. A central engine offers one answer. A newborn Magnetar offers one of the most plausible versions of that answer. The remnant does not just survive the collapse, it becomes part of the explosion's visible power budget. It turns hidden birth physics into observable brightness on much larger scales. The story on the surface is smaller than the story underneath. That line has followed the entire descent, and here it becomes almost literal. A city-sized remnant can help govern the fate of debris millions of times larger than itself. The small object at the center may decide how long the giant event remains luminous. There are even broader implications. Some long-duration gamma-ray bursts and other extreme transients may also involve newborn compact objects acting as central engines. In some cases, the evidence points toward black holes and relativistic jets. In others, especially where sustained energy injection seems necessary, a magnetar remains a serious possibility. The answer seems clear until the event is examined in detail. Then the neat categories blur. The central engine problem becomes one of timescale energy reservoir field strength, ejector mass geometry and survivability. A magnetar can in principle power extraordinary emission, but only if it is born under very demanding conditions and avoids collapsing into a black hole before its energy can matter. Once again, the magnetar is not an easy solution, it is a narrow one. That is exactly why it is so compelling. If the engine works, it tells us that the remnant was born far strong and stable enough to inject power into one of the brightest stellar explosions in nature. The achievement is real, the requirements are brutal, and that in turn loops back to the birth question itself. A magnetar is no longer merely an observational endpoint, it becomes a bridge between hidden compact object formation and the largest visible consequences of stellar death. A violent remnant born deep inside the core may reshape the light curve of the entire explosion outside. A magnetic field assembled in seconds may influence what telescopes see for weeks or months. The compact object becomes a hidden author of brightness, yet even here certainty refuses to arrive cleanly. Some events fit Magnetar engine models well, others do not. Some may mix multiple power sources, some may imitate a central engine through interactions in the ejector or circumstellar environment. That uncertainty is not a weakness in the story. It is part of what makes the story larger. Magnetars matter because they may explain not only what certain neutron stars become, but why some of the universe's brightest stellar explosions look as though death itself is being powered from within. And once that possibility is allowed, the scale of the problem shifts again, because the question is no longer how rare these remnants are in principle. It becomes how many stellar deaths across the cosmos may be taking this route more often than older assumptions ever allowed. Magnetars may not be the freak accidents they were once imagined to be. That is the next enlargement, and it matters because rarity changes meaning. If magnetars are truly only a tiny handful of bizarre remnants, produced under nearly impossible conditions, then they remain fascinating but marginal, the cosmic equivalent of pathological cases. But if the fraction is higher than older assumptions allowed, then the story changes completely. The question stops being why nature occasionally permits such an object and becomes why stellar death so often seems willing to approach magnetic extremity. For years, magnetars were easy to frame as rare outliers, Only a limited number were identified. Their behavior looked unusual enough to justify the category. Their bursts, giant flares, and persistent high-energy emission made them seem like an exotic subclass carved out from the far edge of neutron star possibilities. That picture had an intuitive appeal. Neutron stars were already strange. Magnetars could be treated as the especially strange ones born only in exceptional circumstances, occupying a narrow niche in the compact object zoo. The obvious explanation is that the small observed population proves the underlying birth channel must be extraordinarily uncommon. The real explanation is more dangerous because observed population is not the same as true population. A magnetar is easiest to recognize when it is active nearby, well-timed, and willing to advertise itself through the kinds of emission astronomers know how to catch. But a compact object can spend long periods quiet. A field can be buried. A remnant can resemble another class for years. Activity can come in episodes rather than permanence. The sky is not just full of objects, it is full of selection effects. This is the population problem, and once it enters the story, the old comfort of rarity begins to erode. A magnetar can be missed because it is faint, because it is distant, because its bursts are brief, because its surface field looks less extreme than its internal field, because it is in a quiescent state when no one is looking, or because its behavior overlaps with objects catalogued under different labels. That means the known sample may tell only part of the truth. The remnant may exist without declaring itself clearly enough for easy classification. This is where the scale of the problem changes. We're no longer asking only how to explain the most spectacular magnetars. We're asking how many neutron stars may pass through magnetar-like phases, how many are born with buried or evolving magnetic structures, and how many remain invisible to the category simply because their most revealing episodes have not been caught or have not happened yet. The category begins to look less like a tiny isolated island and more like the exposed peaks of a larger submerged terrain. There are several reasons this matters. First, some objects that look like high-field pulsars or otherwise unusual neutron stars may occupy adjacent evolutionary ground. Second, transient magnetars show that magnetic dominance can become unmistakable only during active episodes, which means the quiet sky may be concealing more potential members than the loud sky reveals. Third, if fullback can bury a field and later allow it to re-emerge, then a newborn magnetar may spend part of its life looking less exceptional than it really is. Fourth, if internal magnetic structure matters more than surface dipole alone, then population estimates based only on the most easily inferred field strengths may systematically undercount the true magnetic burden carried by neutron star remnants. The answer seems clear until the population is examined not as a census of labels, but as a census of hidden possibilities. And once that happens, the implications widen. If magnetars are born more often than once believed, then the conditions needed to create them may not be as impossibly narrow as earlier stories implied. That does not make them ordinary. It makes the birth routes more accessible to stellar evolution than a tiny sample once suggested. Rapid rotation may survive into collapse more often in certain progenitors or binary channels. Strong internal fields may be retained or built more frequently than older models allowed. Fullback-mediated evolution may produce delayed or disguised magnetars that only later become obvious. Multiple channels may together contribute enough births that the total fraction rises even if no single mechanism dominates. This is the deeper reframing. A larger true population does not force one perfect explanation. It strengthens the case that the pathways are plural and that observational incompleteness has been narrowing the story more than nature has. It also changes how the larger sky is interpreted. If magnetars are not vanishingly rare, then their role in powering extreme transients shaping remnant evolution and contributing to the diversity of neutron star behavior may be more central than once assumed. They stop being anecdotal. They become a meaningful branch of stellar death, a branch large enough to matter for how often galaxies produce certain X-ray transients, how some supernovae evolve, how compact remnants are distributed across environments, and how neutron star categories blur into one another over time. The achievement is real, the consequence is larger. A revision in birth fraction is not just a bookkeeping update, it is a change in cosmic emphasis. But the enlargement comes with a cost. The more the population expands, the more the boundaries soften. If many neutron stars may harbour hidden internal fields, if some behave like Magnetars only intermittently, if some are born disguised, and if some pass through Magnetar-like states rather than occupying a perfectly separate box, then the category itself becomes harder to treat as cleanly bounded. Magnetars may be common enough to matter more yet structurally ambiguous enough to resist tidy census. That is the paradox Section 12 has to land. The objects may be less exceptional in number than once thought, but more complicated in identity than older textbooks preferred. And this is not a minor philosophical inconvenience. It cuts directly into the birth problem. If Magnetars are more frequent, then models must account for that without erasing the genuine difficulty of producing such strong magnetic outcomes. If the class is broader, then the mechanisms may be more diverse. If the observations are incomplete, then every theory is arguing with missing members of the population. The story gets bigger but also less settled. Magnetars may be more common than they look, more varied than they seemed, and more important than their small famous sample once implied. Yet that greater importance does not simplify the origin. It intensifies the unresolved pressure around it, because the larger the class becomes, the harder it is to pretend that one clean mechanism, one clean field estimate, or one clean label can finish the argument. And that means the next chamber in the descent is unavoidable, because after widening the scale, the story has to confront its remaining limits directly. The thresholds we still cannot calculate perfectly, the fields we still cannot see fully, and the hidden costs that keep Magnetar birth partly unresolved even now. The closer astronomy gets to Magnetars, the more the origin story begins to dissolve into thresholds that cannot yet be pinned down with total confidence. That is not failure. It is the cost of pushing explanation toward one of the most extreme corners of stellar physics. By this point in the descent, much of the broad shape is visible. Massive stars die. Iron ends the old bargain. The core collapses. A proto-neutron star is born. Rapid rotation may amplify magnetic fields. Fallback may rewrite the remnant. Multiple channels may converge on the same outcome. Hidden internal fields may matter more than surface measurements suggest. Some of the brightest explosions may depend on these compact engines. The population may be larger than once believed. All of that is real. But the closer the argument gets to the exact birth moment, the less neat certainty survives. The obvious explanation is that the remaining gaps are merely details to be filled in later. The real explanation is more demanding. The missing pieces sit near the centre of the problem, because Magnetar birth happens where several brutal unknowns collide, at once the behaviour of ultra-dense matter, the transport of angular momentum inside massive stars, the geometry and survival of magnetic fields during collapse, the amount of fallback after explosion, the threshold between neutron star survival and black hole formation, and the problem of inferring hidden interior structure from limited signals seen far away. These are not decorative uncertainties. They shape the verdict itself. Start with the matter inside the remnant. A proto-neutron star is not made of ordinary substance squeezed a bit harder. It is matter driven into a regime where theory remains strained and observation indirect. The equation of state of ultra-dense matter, the relationship between pressure density and composition at these extremes, helps decide the size, stiffness, and survival margin of the remnant. A stiffer equation of state may support more mass before collapse. A softer one may drive the object toward a black hole sooner. That matters because Magnetar birth requires survival long enough for magnetic amplification, rearrangement, or fallback-mediated evolution to matter. The difference between a neutron star and a black hole can depend on details of matter physics that no laboratory on Earth can reproduce directly. This only looks like a compact object problem. It is also a nuclear physics problem hiding inside a stellar death. Then there is the question of angular momentum before collapse. Rapid rotation may be central in one major birth channel, but predicting how much angular momentum a massive stellar core actually retains is notoriously difficult. Stars lose mass in winds. They expand, contract, mix, exchange material with companions, and transport angular momentum internally through mechanisms that are still being modelled and debated. Magnetic torques inside the progenitor can drain core spin. Binary interaction can restore it. A merger can radically transform it. By the time collapse begins, the core's rotational state may be the outcome of an entire hidden biography. That makes Magnetar birth difficult to predict from surface appearances alone. The remnant inherits not just mass, but the unresolved history of how that mass moved. Magnetic fields themselves are even harder. A field can be compressed, amplified, buried, tangled, wound into toroidal structure, or partially hidden beneath freshly accreted layers. Simulations can explore parts of this process, but the full collapse environment is a nightmare of competing scales. General relativity matters, neutrino transport matters, turbulence matters, rotation matters, resistive and conductive effects matter, the dimensionality of the simulation matters, small-scale instabilities may alter large-scale outcomes. A model can capture part of the truth and still miss the pathway that decides whether the remnant becomes merely powerful or Magnetar-level extreme. The answer seems clear until the computation is forced to represent the actual violence of the event. Then the limits of knowledge become visible. Even fallback, which offers such an enticing second chance in the narrative, is hard to constrain cleanly. How much matter returns depends on the progenitor structure, the explosion energy, the asymmetry of the blast, the circumstellar environment, and the timing of reverse shocks in the ejector. Too little fallback and the remnant may remain ordinary. Too much, and the remnant may disappear into a black hole. Somewhere in between lies a narrow corridor where spin mass loading, field burial, and survival can still combine constructively. The corridor may exist. The width is uncertain. That is a recurring theme here. Almost every route to a Magnetar seems to pass through a threshold so narrow that slight changes in initial conditions can alter the ending completely. Observation does not rescue us as easily as one might hope. Magnetars are bright in some bands, but not constantly. Their burst can be brief. Their quiet phases can be long. The internal field cannot be measured directly. The dipole field inferred from timing is only part of the picture. Supernova remnants age and erase evidence. Progenitor stars are often gone before anyone knows how important they were. Binary companions may be absent, destroyed, ejected, or difficult to identify convincingly. The object that remains is real, but the direct record of its birth is fragmentary. Astronomy is forced into a form of reconstruction that is both rigorous and incomplete, using remnants, timing flare behavior environments, models, and statistical populations to infer a hidden event that no observer truly watched from the inside. This is why Magnetar origin remains partly unresolved despite decades of progress. The science is not weak. The target is brutal. A Magnetar is born where stellar evolution, supernova physics, nuclear matter magnetic amplification, and compact object survival all overlap in seconds. That is a terrible place to demand perfect clarity. Yet the unresolved pressure is also what makes the topic so powerful. Each uncertainty is not merely a hole. It is an active edge where the next discovery could revise the scale of the story again. A better understanding of dense matter could move the survival threshold. Better transient surveys could reveal more disguised members of the class. Improved simulations could show which pathways dominate. New remnants, companion identifications, or early-time supernova observations could connect compact object birth to explosion behavior more tightly than before. The achievement is real. The closure is not complete. Magnetar birth remains one of those scientific problems where the broad outline is convincing and the decisive inner mechanics are still under siege. And that unresolved center matters because it means the final meaning of the story is not just that magnetars are born in extreme stellar deaths, it is that their birth sits exactly at the border where the universe tests how far matter magnetism and gravity can go before one state of reality gives way to another. A magnetar is not just the endpoint of one star's collapse, it is part of a longer economy of death survival recycling and consequence that runs across galaxies and through time. That is the larger scale the story has been approaching from the beginning. At first the problem looked local. A massive star dies, a core collapses, a remnant forms, and in rare cases that remnant emerges with magnetic violence so extreme that it behaves unlike ordinary neutron stars. But once the layers are stripped back, the magnetar can no longer be treated as an isolated curiosity. It belongs to a chain. The progenitor star belongs to a stellar population shaped by metallicity, binarity, mass loss, and prior generations of enrichment. The supernova belongs to a broader ecology of explosions that reshape interstellar gas seed turbulence and alter future star formation. The remnant belongs to the compact object population that later fills galaxies with pulsars, X-ray sources, binaries, merger candidates, and high-energy transients. The obvious explanation is that a magnetar matters because it is extreme in itself. The real explanation is larger. It matters because its birth sits at the junction of processes that connect the private death of one star to the public evolution of whole stellar systems. Start with the most basic consequence. A massive star does not die in isolation from the galaxy that made it. It forms from gas enriched by earlier generations of stars, then returns altered matter and energy back to that environment when it explodes. Even before asking whether the remnant becomes a magnetar, the supernova already participates in a larger cycle of cosmic recycling. The explosion disperses elements forged in the star's interior. It drives shocks into surrounding gas. It can compress nearby regions, stir turbulence, and influence what kinds of stars form afterward. The compact remnant left behind is one product of that cycle, but it is also a continuing actor inside it. A magnetar is part of the returned legacy of stellar evolution, not a detached artifact. And because its internal field and rapid early evolution may shape the transient that surrounds it, the magnetar can alter not only what remains of the star, but how that return to the galaxy unfolds. The compact remnant becomes a hidden term inside the larger budget of stellar feedback. This alone widens the meaning. But the deeper enlargement comes from time. A magnetar's birth may be only one station in a longer itinerary. Some magnetars may live alone and spend the rest of their existence gradually losing rotational energy, evolving magnetically and occasionally flaring. Others may remain in binary systems or may have been prepared by binary histories before birth. A few could occupy paths that later intersect with other compact objects, changing not only their own behavior, but the future of the system around them. This matters because compact objects are not static debris. In binaries, they can exchange mass-alter orbits, survive kicks, or later merge after millions or billions of years of orbital decay. In that broader perspective, the birth of a magnetar is not only a terminal event, it can be the beginning of a second life inside a different class of astrophysical problem. The same remnant that begins as a hidden magnetic engine inside a supernova can later become part of a binary part of a transient part of an X-ray source, or part of a merger pathway that ends in gravitational waves and new matter ejected into space. The story on the surface is smaller than the story underneath. That line now expands beyond the star itself. The star's death is smaller than the system history it enters afterward. This is where the relation to heavier elements and later transients has to be handled carefully, because scale can tempt exaggeration. Magnetars are not required to explain every recycled atom in the universe, and they are not the sole engine behind every bright transient. But they belong to the same cosmic machinery that makes such phenomena possible. Massive stars forge many of the lighter, heavy elements during life and death. Neutron star mergers appear to be major sites for the heaviest R-process elements. Magnetars intersect that larger story, because they emerge from some of the same progenitor channels, can influence certain explosive transients at birth, and may become part of the compact object family that later participates in merger histories. The remnant is not the whole chain. It is one of the most extreme links inside it. That is enough to matter enormously. It means Magnetar formation is not just a question about how a star dies, but about how compact object diversity feeds forward into later astrophysical consequences across multiple timescales. A newborn Magnetar may help power an unusually luminous supernova in the short term. A surviving compact binary may shape later high-energy behavior in the medium term. A compact object merger elsewhere in the galaxy may return neutron-rich ejecta to space in the long term. Different processes dominate different outcomes, but the Magnetar belongs inside the same broad cosmic traffic of death becoming future structure. And there is also a philosophical enlargement that the physics earns. Magnetars are born where several frontiers of nature overlap gravity near its non-black hole limit, matter near nuclear extremes, magnetic fields pushed into astonishing strength, and stellar evolution brought to an irreversible crisis. That makes them more than another entry in a catalogue. They are places where the universe reveals how continuity breaks. A main sequence star through a sequence of ordinary physical laws, followed far enough and under enough pressure, becomes an object whose magnetic field can outmuscle its own crust, and whose birth may influence explosions seen across vast distances. Nothing supernatural has entered the story. The laws did not change, but the regime did. And regime change is one of the deepest themes in nature. Quantity becomes quality. Pressure becomes transformation. A familiar star becomes an unfamiliar state of matter, with consequences that reach far beyond the core where it was born. This is why Magnetars matter at larger scale. They are not merely spectacular, they are clarifying. They show how the universe uses collapse not only to destroy, but to sort branch and create new categories of consequence. Massive stars do not all leave the same kind of future behind. Some produce quieter remnants, some vanish into black holes, some through narrow and still partly unresolved pathways produce magnetic engines capable of altering the visible behavior of their death and the long afterlife that follows it. The achievement is real. The meaning is larger. A Magnetar is one answer to the question of what stellar death can become when gravity does not win completely and matter does not remain ordinary. And that leaves only one step left in the descent, because after moving from explosion to core, from remnant to engine, from isolated birth to cosmic consequence, the final task is to return to the opening image of the bright supernova and say exactly what was really being born inside it all along. The brightest stellar explosions in the universe do not merely mark an ending. In the Magnetar story, they conceal a selection process so violent and so compressed that the true birth happens almost underneath the light rather than inside it. That is the final synthesis, and it returns us to the opening deception with a fuller answer. A supernova looks like the main event because it is the part the universe makes easiest to see. The blast expands, the debris glows, the dead star announces itself across enormous distances in a language telescopes can catch. But the light is not the verdict. It is the evidence that a verdict has already been delivered elsewhere in a collapsing core where mass rotation, magnetic structure, fallback and survival are forced through a narrow set of possibilities in only seconds. That is what a Magnetar really is. Not simply the corpse of a massive star, not merely a neutron star with a more impressive field, but the surviving product of an extreme hidden judgment. Gravity tries to finish the star completely. Matter resists just enough to avoid becoming a black hole. Rotation may concentrate enough energy to drive magnetic amplification. Fallback may rescue or erase the remnant. Internal fields may be built buried, tangled, or wound into forms the surface does not immediately reveal. And if the balance lands in the right place, a city-sized object emerges carrying magnetic stress so immense that the explosion outside is no longer the whole story. The remnant becomes a second event embedded inside the first. That is the deepest reframe the script has been building toward. The supernova is not the magnetar's origin in the simple sense. It is the bright outer shell of a more selective birth process hidden in the center. The obvious explanation is that the star explodes and leaves something unusual behind. The real explanation is that the collapse strips the star down to a final argument over what state matter can survive in how much angular momentum remains available, and whether magnetic energy can be amplified into dominance before gravity takes the remnant all the way down. The Magnetar is the answer to that argument when the remnant survives as a neutron star but refuses to remain ordinary. It is what happens when collapse does not end in silence. It ends in stored violence. That is why Magnetars feel larger than their size. They are tiny by stellar standards, yet they inherit the concentrated consequences of an entire stellar life. They carry the last decisions of the progenitor's structure, the failure of ion-supported fusion, the compression of collapse, the first-second chaos of the proto-neutron star phase, the possibility of dynamo action, the risk and opportunity of fallback, the hidden architecture of internal fields and the long afterlife of bursts flares, an engine-like influence on the debris outside. The object is small, the history inside it is not. In that sense, a Magnetar is one of the most compressed narratives in astrophysics. Millions of years of stellar evolution narrowed to seconds, then locked into a remnant only tens of kilometers across. And yet the story does not shrink with the object. It expands. It reaches into supernova remnants, into the brightest transients, into population questions, into the uncertain physics of ultra-dense matter, into the broader ecology of stellar death across galaxies. The achievement is real. The cost is total. A star has to fail in nearly every old way before such a remnant can exist. This is what makes the opening image look different now. The bright explosion is still magnificent. It still tears a star apart. It still fills space with debris and light. But it is no longer mistaken for the whole truth. The flash is an announcement, not an explanation. The explanation lives in the hidden center where the star stops being able to support itself and begins being sorted by thresholds more severe than anything in its long previous life. Will the core collapse straight through into a black hole? Will it settle into a more ordinary neutron star? Will rapid rotation, magnetic amplification and survival combine into something more extreme? Those are the real questions being answered while the sky is still busy, dazzling distant observers with the blast. The story on the surface is smaller than the story underneath. That sentence repeated in different forms throughout the descent becomes the final key. It is true of the supernova relative to the core true of the dipole field, relative to the interior true of the catalogue label, relative to the hidden formation history, and true of the compact remnant relative to the wider cosmic consequences it may later influence. A magnetar is what remains when all of those smaller stories are forced to yield to a deeper one. Not the story of brightness alone, but of compression selection and survival under impossible pressure. Not the story of a dead star simply cooling, but of a remnant born with enough buried energy to go on altering the aftermath of its own creation. Not the story of spectacle, but of a hidden engine. And that is why Magnetars are so compelling in the end. They reveal that some of the most spectacular things in the universe are not the things that matter most, only the things that make the hidden matter visible. The explosion is what we see. The Magnetar is what the collapse decides. The light fills the sky, but the true birth happens in the dark where gravity, matter and magnetism force one of the universe's brightest deaths to produce one of its most violent survivors. What makes Magnetars unforgettable is not just that they are powerful, it is that they expose the hidden hierarchy inside catastrophe. A supernova looks like the climax because it is the part the universe throws into the open, the light, the debris, the spectacle, vast enough to be seen across galaxies. But the deeper truth is more severe. The light is only the public surface of a private judgment. Deep inside the collapsing core, before the explosion has finished announcing itself, matter is forced past familiarity. Gravity presses toward total victory, and a remnant is selected under conditions so extreme that even survival is already a kind of exception. That is why a magnetar feels larger than its size. It is not simply a dead star. It is the compressed outcome of a long stellar life, a failed balance against gravity, a collapse measured in seconds, a narrow escape from black hole finality, and a magnetic inheritance that may be amplified, buried, twisted, and unleashed for years afterward. The object is tiny in cosmic terms. The pressures that create it are not. Neither are the consequences. In the end, the story is not really about one exotic subclass of neutron stars. It is about what the universe does when familiar structures are driven beyond their limits, but not all the way into disappearance. Sometimes collapse erases, sometimes it leaves behind a quieter remnant, and sometimes, through a combination of timing, spin field growth fallback and survival, it leaves behind a magnetic engine that can keep disturbing the aftermath of its own birth long after the parent star is gone. So the brightest explosions are not merely endings. In the most extreme cases, they are acts of selection. They tear a star apart, but they also reveal that death can produce a remnant more violent than the life that came before it. The flash is the announcement. The Magnetar is the decision.